I'll actually pick up the recording for this. All right, so for this chemical reaction, why is it particularly useful? We're starting with a ketone, we ended a carboxylic acid. The carboxylic acid is not as synthetically useful as the ketone. This seems like a really bad idea. Right? So why do we do it? It is technically named. Right? It's named as the haloform reaction as a class. This specific one is known as the iodoform reaction. Right? Why do we talk about this chemical reaction?
Because for the iodine, carbon iodine, holding the will come from a negative carbon, I guess.
Okay? We do form a negative carbon, but is that negative carbon synthetically useful? It immediately picks up a hydrogen and shuts down its reactivity. We form the haloform. Chloroform is another example of this. Chloroform is classically used as a solvent. In fact, that's our solvent for almost all of our NMR. Right? And as a solvent, what does it do chemically? Nothing. All it does is allow things to mix. It doesn't do anything chemically. Okay? So forming that iodoform structure, not particularly useful. Officially, we aren't at our final product, right? Because our final product, this is the carboxylate. We follow it up with H3O+. Okay, for drawing it up on the board, they kept throwing the H3O+ is the very last thing. So we get our carboxylic acid. Okay. Why is this useful? It's useful because we can add a little piece of information. HCI3 is a solid. And if we want to get extra specific, this is a yellow solid. I would write it in yellow, except you wouldn't be able to see it. Why is that important? I'm curious now. I'm going to try and write it in yellow. Doesn't look bad on my screen. Oh, it's not bad. Why do I care that I have a yellow solid?
Conjugation, right? Isn't that what dictates color?
So conjugation is something that comes up with color. We're not getting any conjugation when you look at the iodoform, unfortunately. So the color's coming from a different aspect behind that. Probably looking at our favorite d orbitals with the iodine, doing some weird, nasty stuff. That's about all I got. Let's add a little bit more information. Okay? At the same time, we're going to remove a bunch of stuff because ultimately all of this, the how it happened, was very irrelevant.
If you're running the reaction, the yellow shows how the reaction happened.
Okay, we're seeing a change in color. Okay, and not only a change in color, a change in phase. This is a really good sign that a chemical reaction happened. But this is OChem. Isn't that exactly what we study? Because in everything we've done a chemical reaction. Yeah. Right wavelength. Can you push on that a little further?
Synthesized product.
We just said the product was useless.
Is it to find, like similar to the lab, where we find the wavelength of the concentration?
No.
Maybe
I'll add a little bit more information here. Time, this is usually less than 5 minutes. In fact, you're probably on the order of about a minute. Why would that matter? There's the last clue. What was that clue? What do we do with that clue? I erased the starting material. Why is this relevant?
So the yellow shows if you have no more starting material? Or have less?
No.
Does it correspond with it?
Okay. If I take sodium hydroxide and iodine and I add it to an unknown sample, if I see a yellow precipitate, what do I know?
And it's acidic?
I know the product is an acid. I don't care about the product. I didn't erase the product. If I add sodium hydroxide and iodine to something out here and I see this precipitate, what does that mean about what was there?
That it was acidic.
Okay? But not just any ketone, a very particular ketone.
Carboxylic acid.
Starting with a ketone. To get the ketone, what did we have to do? You can look at your mechanisms. To get the CI3, what kind of ketone did we have to have? I had to have a CH3 next to that carbonyl. That stuff in red, I would know is present. If I started with, I don't know my nomenclature well enough, so let's go just 2 benzene rings. That's a benzene ring, trust me. Is this going to give me that yellow precipitate? No, why not? It doesn't have those alpha hydrogens. What if I had this structure?
Same problem. There's no alpha. Well, there's alpha hydrogens.
There are alpha hydrogens. How many alpha hydrogens did I need? 3. So if I don't know what I've produced, and I suspect there's a carbonyl, what I can do is drop some sodium hydroxide and iodine in with it, stir it around real quickly, and look for that yellow precipitate. If I see a yellow precipitate, that means whatever that unknown thing was, yes, indeed had a carbonyl, and it had a CH3 immediately next to it. I know that to be true. This is what's known as a classification test. Okay? These used to be incredibly common. We've actually already talked about classification tests in this class. The very first unit we mentioned one. Anybody remember what it was? It's a long shot, throw it out there, see what happens. Began with an L. Lucas. Okay, the Lucas reagent was zinc chloride and hydrochloric acid. Okay, what that produced was a zinc oxide. That zinc oxide was a white precipitate, which told us we had a tertiary alkyl chloride to begin with, or tertiary alcohol, to begin with. We get some information about our starting structure by running a very quick chemical test. Why would we run chemical tests if we had NMR or IR? What do NMR and IR tell us?
Bonds.
Okay. IR tells us about the bonds that are present. What does NMR give us? Pretty darn close to the whole flippin' structure. Why do I do classification tests if I have spectroscopy? You don't. Okay? Technology has advanced enough and has dropped in cost enough that we don't need to run classification tests anymore. We can just run spectroscopy. Okay? So why do we talk about classification tests? Why do we talk about the world wars? Why do we talk about the French Revolution? Okay? Those were aspects of the history of organic chemistry that are still part of the culture and still ingrained in a lot of chemists, particularly 2 cases of chemists. Any guesses what organic chemists are ingrained with classification tests? Old ones, yeah, old ones are ingrained in it. Okay, you've got a lot of old chemists referencing classification tests. Who else? Trying to say I'm old? Not quite sure where that one's going.
Professors?
Why does that don't have access to the spectroscopy stuff?
The reason you get rid of the classification test is because you have the technology. If you don't have the technology and you need to figure out structure, what do you need to do? You use the classification tests. Okay, so labs that do not have the spectroscopy or the technology rely on the classification tests. So if you are learning chemistry, depending on where you are located, you will see a different emphasis on these individual classification tests. Okay? Which is why the textbooks then also have to talk about them and address them and bring them forward. Okay? They could do a better job pointing out why we use them and what they're used for, okay? But that's the intent. Okay? So if you're looking at South America or even Africa, okay, some Asian countries, okay, as well have the same issue. They don't have the funding for the labs, okay, or the lab equipment, but they do have enough funding to get a hold of chemicals. They can run classification tests to get some structural information. And because they have access to those tools, their students know more about them. That's where it's coming from. Kind of, sort of? And since ACS writes a final that's supposed to encompass all of chemistry, it's going to include classification tests also. Are there a whole hell of a lot of other classification tests? Yeah, because the whole point was to figure out the whole goddamn structure, which means there's a ton of classification tests. Are you going to see them all? No. But you're going to see a few pop up. This is one that pops up a lot. Okay? I've even seen this one pop up in Gen Chem 152. Because you can use it to titrate in the sodium hydroxide to get a feeling for how much of the methyl ketone was present. I believe is how they used it. I honestly don't remember. Okay? So kind of neat. Theory, I answered your question and then just beat the living daylights out of it with a whole bunch of extra information. Okay. After that, where do you guys want to go?
I just completely forgot that water was
And-
part of the reaction.
Ta-da! There's the answer. That's for the recording. Okay. You forgot that water is part of the...
Yeah, I didn't review the oxidation agent.
You forgot that water...
I guess I didn't read either.
Okay? And I understand that. Okay? That's going to happen. As you go through and take a test, you're going to try and skip as many things as possible. Be as careful as you can behind that. Right? There's a lot of information that sits within those details, and if you miss them, you can very easily end up selecting the wrong answer. Okay? We'll delete that. You said question 5?
Yeah.
See, is it going to do it? Cool, I did it. With each set, you can make me scroll. Stupid. You haven't even attempted it. Yeah, okay. Cool. You know the best place to attempt things as a group?
On the board.
Yeah, let's go. Okay, I'll start writing up the, well, I'm going to try and write up the reagents. Hopefully there isn't a whole bunch of them. So we got lithium hydride. Oh, sodium hydroxide. Oh, wow, how many of these are there? Okay. Ooh, and then diball. Ugh.
No, that's all right. It doesn't need to have the race again anyway.
Anybody know what diball is?
Eyeball? I thought you said eyeball.
So I'm going to take that to mean no. I'll draw the structure up so you've got access to it. This is actually kind of a neat way of addressing it. Assuming I can draw it right. Nope.
It looks similar anyway.
There's 2
And we'll go ahead and pause the video while people try and work it out. Okay, so if we go through and look at that first reaction with the lithium aluminum hydride, lithium aluminum hydride is a standard reagent you've already seen. That's what you should be saying to yourself every time you run the reactions in this unit. I've already seen this reagent, because you have. Okay? You've seen them all in Unit 2. As I say that, there's already an exception on this slide. But for the most part, you've seen the reagents. Okay? And so what happens with lithium aluminum hydride is it's active as an H-. If we acknowledge that we have, I guess we'll color code it slightly differently, an H-. If we acknowledge that our starting material has a partial positive, we're going to have the H- come in, put the hydride on. Okay? When that hydride comes on, we would form our kind of intermediate structure. This intermediate structure is different than what we saw in Unit 2 because we have that extra oxygen CH3 on there. That extra oxygen changes the chemistry a little bit, and once we've added that hydride, what we would end with would be a hemiacetal. The hemiacetals, as we learned in the last unit, are unstable, okay? And they rapidly revert to the carbonyl. In the process of reverting to the carbonyl, you're going to eject that OCH3- as a leaving group, and you get an aldehyde. Okay? That's the lithium aluminum hydride reaction. The problem with the aldehyde is that, as we learned in Unit 2, what does the aldehyde do with lithium aluminum hydride? It continues to react and takes us down to the alcohol. But before we can officially push into that, the question that we need to ask is, should it do that? Okay? And that's a much harder question to deal with. What we're actually asking about there is looking at our intermediate product, comparing it to our starting material, the aldehyde versus the ester. If the ester is more active than the aldehyde, the lithium aluminum hydride will react all the way, theoretically, with the ester, leaving you with the aldehyde. So once this reaction runs one time, we've got aldehyde and ester floating around. Where does the lithium aluminum hydride, quote unquote, choose to go? Okay? And for people that care, we're not trying to anthropomorphize or whatever that stupid word is, or personify them. Okay? What we're trying to address is the reactivity difference between these. Which one is more reactive, the aldehyde or the ester? Okay? And then gut reflex that everybody jumped on was the ester. The ester is more reactive because that green oxygen can withdraw electron density away from the carbonyl, making that ester carbonyl more positive. And the explanation you're using there is induction. Okay? It keeps coming up, and I keep telling you, stop using induction as an explanation. Okay? Because it is very rarely ever induction. If we take a step back into our tree and look at resonance, that oxygen has lone pair electrons which donate into the carbonyl, which stabilizes the partial positive. Because that positive is more stable, the aldehyde missing that reactivity is more active. Okay? Which can set us up for a little bit of a summary that we could draw on our left. We could go through and say the aldehyde is higher in energy than our ester. Okay, and I'm going to have to fix that drawing here in a second. Okay, so the aldehyde continues to react. We get to the alcohol. We drop in the hydroxide. Hydroxide is going to run the same process. It goes through and attacks, and it forms a wicked tetrahedral intermediate with 3 very electronegative oxygens around it. Both boards drew that up. That structure is incredibly unstable. The oxygen, we're looking at effectively an uber hydrate, if you will. Okay, that negative oxygen crashes back down, kicks out one of our other oxygens as a leaving group. Why does it preference the, if we look at my drawing, the green OCH3 and not the OH that attacked? Okay. If we look at the intermediates that form, in the case of the purple, right? I said the green OCH3. Why, when these electrons come back down, does it preference the hydroxide or does it preference the ester? Which one's better? Well, how do we decide? Where do we start?
Try both.
Charge. Charge on what atom? Oxygen and oxygen. Is there a difference in charge? No. How about size? Electronegativity? Resonance? Induction? Maybe. Okay. Is there really a difference? No. Which means?
Go with the one that actually pushes the reaction forward.
Okay. We got a couple of choices. We could just cheat and say, why would we do something that doesn't go anywhere? So we're just going to push it forward. It is a heavily equilibrium-dependent reaction. The way we force it to go through and continue on to the products is by adding a ton of the hydroxide to overwhelm it, so that the majority of the systems are ejecting the ester, that green oxygen up on the screen, instead of the hydroxide. Okay? After that reaction, most people stop with our carboxylic acid. They go, oh, great, there's a product, and we're good to move. The problem is that that's equilibrium dependent, which means I'm not getting a lot of that product. And yet when I run this reaction, I actually get a vast excess of the carboxylic acid product. How could that possibly be true if it's looking at random chance and equal probabilities for those leaving groups? Because what we're not acknowledging is that we're in a strongly basic environment that immediately reacts, goes through and forms the carboxylate. The carboxylate is resonance stabilized. That step is irreversible. But you're like, but that's not in the product. Well, what was step 2 there for?
H plus.
Okay? And so mechanistically, this is a frustrating reaction to run, because you're like, I formed the product. You want me to continue past it and then go right back to it? Yes, because that's what happens in the mechanism. Okay? Yes, that's frustrating. I'm sorry. There's nothing I can do about it. That's how the chemistry works. Okay? If we move to the last one, dibol, okay, diisobutyl aluminum hydride. Okay? If we look back to that, some people acknowledge, well, that's an aluminum hydrogen bond. We've seen that before with lithium aluminum hydride. Shouldn't the hydride act as a nucleophile? Yes, absolutely. And in fact, that was one of the things that I pushed back when we talked about the lithium aluminum hydride and sodium borohydride, is acknowledge as long as you have that bond, you have a hydrogen nucleophile. So it is absolutely a nucleophile. Okay? So it will go through and do this reaction. And just like with our top case with the lithium aluminum hydride, it goes through to form the aldehyde. Right? In the top case, the aldehyde was more active than the ester, and therefore it continued to react. Isn't that the exact same boat we're in with the dibol? Yeah. And yet, it doesn't continue. We get a couple different ways that we could try to BS our way through why it doesn't continue. Okay? The first and foremost is, I believe, Abby, I think you said it somewhat decently. What was your explanation for why you think it does something different?
I don't remember anymore.
That's fine. Okay. If it does the same thing as lithium aluminum hydride, why do we have the reagent?
Oh, that's why.
Okay? So we can use that kind of flow and logic of what would be the meaning behind that. Okay? And there are plenty of reasons that we would switch out reagents that aren't chemically relevant, because we could talk about safety or toxicity or different aspects like that. This isn't one of those cases. This is literally because we've modified that structure enough that it only reacts with esters. So once the structure reacts with the ester, the aldehyde structure is somehow impinging and preventing the reaction with the dibol reagent.
How so?
Okay.
Is it?
I would love to be able to give you a more in-depth answer, but we're out of time, so sorry. I mean, we are out of time, but I actually don't have a better answer.
You don't know, or is
I
it
don't
just
know.
so? Oh, okay.
I don't know. Okay. So, and there is another one. It's some T-butoxide structure or T-butyl structure, I think. Okay. Those two extra reducing reagents you should memorize, because the explanation for why it doesn't react is not a straightforward, easy explanation, which means spending the time to figure out the why on that isn't worth the investment. You've got enough other BS to deal with, shift the other BS and let that stuff slide. Okay? If it is something you're interested in, we can poke at it. Cardi might go through and explain some of the details behind it. The half-assed answer I go through and do is say, those are isobutyls, and isobutyls are sterically hindered.
Fuck you.
Okay. I don't know that I like that explanation because of how the reaction is functioning. It isn't a sterically hindered system. So using that is kind of a half-assed explanation. Kind of. It is fully a half-assed explanation.
What to say.
Okay.
It's like if there's no history.
So with that, I am going to stop the recording. And sorry, we talked a little bit too long to the